Phosphine is the compound with the chemical formula penthouse 3. It is a colorless, flammable, toxic gas. Pure phosphine is odorless, but technical grade samples have a highly unpleasant odor like garlic or rotting fish, due to the presence of substituted phosphine and diphosphane. With traces of P2H4 present, penthouse 3 is spontaneously flammable in air, burning with a luminous flame. Phosphines are also a group of organophosphorus compounds with a formula 3P. Organophosphines are important in catalysts where they complex to various metal ions. Complexes derived from a chiral phosphine can catalyze reactions to give chiral, enantioenriched products. History: Philippe Gingembre, a student of Lavoisier, first obtained phosphine in 1783 by heating phosphorus in an aqueous solution of potash. Perhaps because of his strong association with elemental phosphorus, phosphine was once regarded as a gaseous form of the element, but Lavoisier recognized it as a combination of phosphorus with hydrogen and described it as phosphadihydrogenase. In 1844, Paul Tharcopyright Nard, son of the French chemist Louis-Jacques Tharcopyright Nard, used a cold trap to separate diphosphine from phosphine that had been generated from calcium phosphide, thereby demonstrating that P2H4 is responsible for spontaneous flammability associated with penthouse 3, and also for the characteristic orange-brown color that can form on surfaces, which is a polymerization product. He considered diphosphine a Euro-unregistered trademark S formula to be penthouse 2, and thus an intermediate between elemental phosphorus, the higher polymers, and phosphine. Calcium phosphide produces more P2H4 than other phosphides because of the preponderance of PP bonds in the starting material. The name phosphine first appeared in combined form in 1857. The gas penthouse 3 was named phosphine by 1865. Structure and properties: penthouse 3 is a trigonal pyramidal molecule with C3V molecular symmetry. The length of the pH bond is 1.42 The H-pH bond angles are 93.5 degree. The dipole moment is 0.58 d, which increases with substitution of methyl groups in the series, CH3 penthouse 2, 1.10 d. 2pH, 1.23 d. 3p, 1.19 d. In contrast, the dipole moments of amines decrease with substitution, starting with ammonia, which has a dipole moment of 1.47 d. The low dipole moment and almost orthogonal bond angles lead to the conclusion that in penthouse 3 the pH bonds are almost entirely pi-fluorine, P, A-C fluorine, H, and phosphorus 3's orbital contributes little to the bonding between phosphorus and hydrogen in this molecule. For this reason, the lone pair on phosphorus may be regarded as predominantly formed by the 3's orbital of phosphorus. The upfield chemical shift to the phosphorus atom in the 31p NMR spectrum accords with the conclusion that the lone pair electrons occupy the 3's orbital. This electronic structure leads to a lack of nucleophilicity and an ability to form only weak hydrogen bonds. The aqueous solubility of penthouse 3 is slight. 0.22 milliliters of gas dissolve in 1 milliliter of water. Phosphine dissolves more readily in nonpolar solvents than in water because of the nonpolar pH bonds. It is technically amphoteric in water, but acid and base activity is poor. Proton exchange proceeds via a phosphonium ion in acidic solutions and via penthouse 2 at high pH, with equilibrium constants Kb equals 4 10^28 and Kz equals 41.6 10^29. Phosphine burns producing a dense white cloud of phosphorus pentoxide, 2 penthouse 3 plus 4O2 a P2O5 plus 3 hours 2O. Preparation and occurrence: phosphine may be prepared in a variety of ways. Industrially it can be made by the reaction of white phosphorus with sodium or potassium hydroxide, producing sodium or potassium hypophosphite as a byproduct. 3KOH plus P4 plus 3 hours 2OA 3KH2PO2 plus penthouse 3. Alternatively, the acid catalyzed disproportioning of white phosphorus may be used, which yields phosphoric acid and phosphine. Both routes have industrial significance. The acid route is preferred method if further reaction of the phosphine to substituted phosphines is needed. the acid route requires purification and pressurizing. It can also be made by the hydrolysis of a metal phosphide, such as aluminium phosphide or calcium phosphide. Pure samples of phosphine, free from P2H4, may be prepared using the action of potassium hydroxide on phosphonium iodide. Phosphine is a constituent of the atmosphere at very low and highly variable concentrations. It may contribute significantly to the global phosphorus biochemical cycle. The most likely source is reduction of phosphate in decaying organic matter, possibly via partial reductions and disproportionations, since environmental systems do not have known reducing agents of sufficient strength to directly convert phosphate to phosphine. Phosphines. Related to a penthouse 3 is the class of organophosphorus compounds commonly called phosphines. These alkyl and aryl derivatives of phosphine are analogous to organic amines. Common examples include triphenylphosphine 3P, and BINAP, both used as ligands in homogeneous catalysis or trisopropylphosphine. Phosphines are easily oxidized to phosphine oxides as exemplified by the directed synthesis of a phosphor crown, the phosphorus analog of an aza crown, where it is not possible to isolate the phosphine itself. In step 1, diphosphanoethane coordinates to a ferrocene containing additional carbon monoxide ligands and an astenitrile ligand. The next step is a hydrophosphonation with trivinylphosphine followed by alkylation with ethyl bromide and hydrogenation with hydrogen over palladium on carbon. In the final step the ion template is removed by bromine, but oxidation of the phosphine groups is unavoidable. When modified with suitable substituents as in certain diets of phospholines, the polarity of the pH bond can be inverted and the resulting phosphine hydride can reduce a carbonyl group, as in the example of benzophenone, in yet another way. Applications. Organophosphorus chemistry. Phosphine is mainly consumed as an intermediate in organophosphorus chemistry. In an illustrative reaction, formaldehyde adds in the presence of hydrogen chloride to give to trachis, hydroxymethyl, phosphonium chloride, which is used in textiles. Microelectronics. Small amounts of phosphine are used as a dopant in the semiconductor industry, and a precursor for the deposition of compound semiconductors. Fumigant. For farm use, pellets of aluminium phosphide, calcium phosphide, or zinc phosphide release phosphine upon contact with atmospheric water or rodent stomach acid. These pellets also contain agents to reduce the potential for ignition or explosion of the released phosphine. Because the previously popular fumigant methyl bromide has been phased out in some countries under the Montreal Protocol, phosphine is the only widely used, cost-effective, rapidly acting fumigant that does not leave residues on the stored product. Pests with high levels of resistance toward phosphine have become common in Asia, Australia and Brazil. High-level resistance is also likely to occur in other regions, but has not been as closely monitored. Genetic variants that contribute to high-level resistance to phosphine have been identified in the dihydrolipoamide dehydrogenase gene. Identification of this gene now allows rapid molecular identification of resistant insects. Safety. Phosphine gas is denser than air and hence may collect in low-lying areas. It can form explosive mixtures with air and also self-ignite. Phosphine can be absorbed into the body by inhalation. Direct contact with phosphine liquid although unlikely to occur may cause frostbite, like other cryogenic liquids. The main target organ of phosphine gas is the respiratory tract. According to the 2009 U.S. National Institute for Occupational Safety and Health Pocket Guide, and U.S. Occupational Safety and Health Administration regulation, the 8-hour average respiratory exposure should not exceed 0.3 ppm. NIOSH recommends that the short-term respiratory exposure to phosphine gas should not exceed 1 ppm. The immediately dangerous to life or health level is 50 ppm. Overexposure to phosphine gas causes nausea, vomiting, abdominal pain, diarrhea, thirst, chest tightness, dyspnea, muscle pain, chills, stupor or syncope, pulmonary edema. Phosphine has been reported to have the odor of decaying fish or garlic at concentrations below 0.3 ppm. the smell is normally restricted to laboratory areas or phosphine processing since the smell comes from the way the phosphine is extracted from the environment. However, it may occur elsewhere, such as in industrial waste landfills. Exposure to higher concentrations may cause olfactory fatigue. Deaths have resulted from accidental exposure to fumigation materials containing aluminum phosphide or phosphine. See also, diphosphane, H2PPH2, simplified to H4P2 diphosphenes, R2PPR2, R2P, CH2, NPR2. Diphosphine, HP equals pH, diphosphenes, RP equals PR. Phosphine oxide, R3P equals O, phosphorane, PR5, R3P equals Cr2, phosphonite, P, or, R2, phosphonite, P, OR, 2R, phosphite, P, OR, 3, phosphonate, R2P, RO, O, phosphonate, RP, RO, 2O, phosphate, P, RO, 3O. References. Further reading, Fluck, E. The Chemistry of Phosphine. Topics in Current Chemistry. Fortschritt der chemischen Forschung 35, 1 €64 doi, 10.1007/BFB00513558. ISBN 3-540-06080-4. WHO. Phosphine and selected metal phosphides. Environmental Health Criteria 73. Geneva, joint sponsorship of UNEP, ILO and WHO. External links, International Chemical Safety Card 0694, CDC, Phosphine, NIOSH Workplace Safety and Health Topic.